Hello everyone. These projects really are an amazing way to push my boundaries and get to try some new things I couldn't even have imagined a year ago. Today I'm hooking up a 10-bit 20 megasample per second ADC to the 50-year-old CPU we know and love from the Ataris, Commodores, early Apple computers and so many others, the 6502. If it wasn't for some very real physical limitations that would give the modular software-defined radio I'm building a simultaneous 20 MHz RX bandwidth, enough to capture the whole FM broadcast band at once, putting it on par with high-end SDRs like the Hacker F1. But of course, we do have to deal with the very real physics, and things don't always go according to plan. That's usually part of the fun, and sometimes things take a bit longer than I would have hoped, and that's just life. And if you're wondering, life is pretty good. And since it's that time of year, I'd like to take this opportunity to wish you and your loved ones all the best wherever you may be in the world. In my video about the PhaseLoom, you might recall I just hooked it up to a sound card, which gave us 44.1 kHz of complex bandwidth out of the SDR. In the last video about the PhaseLatch Mini, I managed to get a bit over 200 kHz into the computer, which was pretty good for a cheap microcontroller which happened to have a somewhat suitable dual ADC. But I kinda knew from the start I wanted something beefier, something real, something with a theoretical bandwidth 100 times better than the PhaseLatch Mini. So for today's project, I've decided to skip the Mini and make an analog to digital converter board with a 20 MHz dual 10-bit ADC. Isn't that expensive, you might ask? Well, I was browsing LCSC looking for ADC candidates, as one does, and I just happened to stumble on this HT9201. Not only is it a 10-bit 20 MHz ADC, it also happens to be straight binary parallel with both channels muxed to the same output pins, which is absolutely perfect for interfacing with a 6502 bus, allowing us to put the two channels straight into the memory map. And it's suspiciously cheap. And it is suspiciously similar to the AD9201 from ADI. It's clearly marketed as its own product and not a fake clone though. Since this is 90s tech, my guess would be the patent has lapsed and the IC has been cloned. I'd like to know how you feel about clones like this in a comment below. Myself, I'd probably pick the original if I was making thousands of boards, since the price difference goes down quite a bit with quantity. But for this, I don't mind trying out the one from HTC Semi. Who knows, it might even be a licensed second source. And speaking of source, I got the boards manufactured by JLC PCB, who very kindly keeps sponsoring these videos. JLC PCB makes PCB fabrication and assembly easy, affordable, and reliable. To have a brand new design manufactured and shipped to you in just a week is an invaluable resource with bringing new designs to life. I've used JLC PCB for years and they've always made it super easy to get things made. The website is easy to figure out, their pricing has made design prototypes super affordable, and they've always been ready to help, even when I try things on the edge of what's possible. If you haven't tried them yet, you can get your first PCB for just $2 and get $70 in coupons. If you like things easy, affordable, and super reliable, then JLC PCB is for you. Thanks to them, I not only get sponsored boards, I also get a reliable partner for making these projects happen. You might notice I also designed this board as an Arduino shield like the PhaseLoom, which does the IQ mixing and frequency selection, unlike the PhaseLatch Mini I designed as a separate board. That's because I intend the design to be modular, so it's easy to swap out parts and swap in upgrades. Usually, Arduino shields are a one-at-a-time thing, but if I add stacking headers to this new PhaseLatch, I can mount the PhaseLoom on top of it and make it all a bit more compact. I still have to pass the RF signals between the boards using the SMA connectors, but that's probably better for signal integrity reasons anyway. I always find it easier to mount and solder the headers using another shield or the Arduino itself to hold them in place. So if I plug in the stacking headers, we get to see how our little SDR sandwich is going to look, even though it isn't soldered yet. The male pins look like they're a bit long, but I think that's actually to leave space for the plastic spacers we usually see on pin headers. Let's take it apart again though, as we're missing the magic that hooks it up to the 6502 bus. Usually, the Arduino Shield form factor boards I make are more or less compatible with a normal Arduino Uno, as well as my 6502 based 6501. The PhaseLatch HERE is a bit different, as it's the first of my shields to take advantage of the direct access to the 6502 buses and control signals on the 6501 revision 1. I haven't mounted the sockets on this 6501 though, so let's do that too. Since we're already hooking up the ADC straight to the 6502 data bus directly, we can read 8 bits of ADC data in a single instruction, which very technically means the 6502 can read the ADC at 2 megabits per second since it's clocked at 1 megahertz and takes 4 cycles for an absolute LDA instruction. We can even up that to 4 megabit per second since the 6502 rarely has a problem running at 2 megahertz. You might notice I consistently call it a 6502 even though the package very clearly says 6507. The discrepancy comes from the fact that I'm talking about the actual IC, or the architecture, and not the plastic package. And that's because every single IC put in a package numbered 6502, 3, 4, 5, 6, or 7 had the exact same silicon integrated circuit. The only difference being which signals got a bonding wire connected to a package pin and which didn't. So from my perspective, they're all 6502 ICs up until the number 6510, which had features added. If we open up the package, we'll see the 6507 does indeed have an A15 address line and an IRQ signal. They're just not connected to a pin on the DIP, because the crystal it was cut from didn't know it didn't need those features. So if it has a 6502 IC, I'm calling it a 6502 unless I'm talking about the plastic carrier. Now, where were we? Yes, with the 6502 bus and control signal pins sandwiched in, we can start soldering them in place. And for that, I'd like to show you one of my favorite new toys that Fnirsi sent me. You might think it looks a bit like a vape pen, but it's actually a really good soldering iron. It's called the HS02 and the box has the iron and everything you need to get the job done, but I also got an external 100-watt power supply, which I recommend getting with it since not all USB-C chargers are created equal. And this one comes with 12 volts at 3 amps, which I believe is the primary supply for the iron via USB-C. It has a variety of tips, small, big, chisels, and so on. It has a refillable spool for the tin, some copper wool for tip cleaning, and a little compartment for a sponge. And of course, what appears to be a sturdy, burn-proof USB-C cable. And one of the best parts, it heats up to 330 degrees Celsius in only 12 seconds. This is not even sped up, it's real time. I did get the kit for free, and I'm not being paid to say this. Fnirsi just sent it to me in addition to a different product with no strings attached. But I do get a commission if you use the discount coupon code in the description. That said, it's a bit hard to contain my excitement. It's a surprisingly well thought out travel kit, and I have a feeling it'll take the place of my desktop soldering iron permanently. The soldering job here I will speed up a bit as we have other things to talk about that's a bit more interesting. The stacking headers feel a bit weird to solder on the wrong side, but it's pretty easy to get done. But I'll have to be careful not to put too much solder if I want to put the plastic spacers on top of the pins sticking out afterwards. The ADC has a lot of options, and I've left most of them available, like changing the reference voltage, doing differential input instead of single-ended, and so on and so on. But all you really need to do to get the board working is to add a few jumpers for power and the address input and clock. The needed jumpers are called JP1, JP10, and JP19 on the board. I haven't pre-configured them on the PCB because I am pretty sure easily swapping the supply voltages will come in handy. No spoilers. With everything in place, it's time for a smoke test. The good news is the power LEDs on the board for both 5 and 3.3 volts light up, but very unfortunately the 6501 refuses to start with the shield attached. I didn't even get to this part yet, but I guess we'll have to skip ahead of it. You might have noticed the 9201 ADC wasn't the only major chip on the board. And that's because I decided to add a bit of extra RAM to the 6501 while we were already interfacing with the buses, because very simply put, we're not going to be doing a lot of digital signal processing, or software-defined radio for that matter, on a 6502 with only 100 bytes of RAM available. So by adding a few kilobytes more, we're greatly increasing what this SDR can do without asking for another computer to do the heavy lifting. But unfortunately, I messed up. I've been so focused on the JEDEC standard pinout for the thousands of 28-pin ROMs and RAMs that I saw a 28-pin chip and assumed the same layout. Well, assuming after verifying it's in the datasheet even. But what I missed was the pin 1 dot in the datasheet for the TSOP28 package wasn't even a pin 1 dot at all. It was just a manufacturing dimple. KiCad wasn't much help either, as it didn't even have the rotated TSOP pinout with pin 1 in the middle of the package in the standard library at all. So I might have messed up pretty bad, but I do feel a little bit set up to fail. We're lucky nothing started smoking though. Only one thing to do about this though, as not a single pin is in the right place. A bit of cleanup with the chisel and we should be ready to try again. And luckily, the 6501 survived being hooked up to all sorts of nonsense and is happily blinking its heartbeat again. But what do we do now? The RAM we need is a bit hard to debug to the board, and a dip-sized one won't quite fit either. If we're sticking with the plan, we are going to need some RAM. So I guess we're back to using a breadboard. Nothing wrong with that. But the whole idea of making it compact kind of goes out the window. I guess we'll need a revision. Since we're moving RAM to the breadboard, it's easier to add a quad NAND gate than to use the existing ones on the PhaseLatch board. By the way, the reason we need the NANDs at all is because the 6502 has a tendency to write random addresses in RAM if the write enable isn't gated by Phi0. In other words, only allow writing the RAM when the 6502 is ready. I've been going a bit back and forth with how to drive the clock from the 6502, but for now I've settled with the simplicity of simply using a GPIO from the 6532. Since the PhaseLatch isn't hooked up to the 6532 any longer, the easiest way to handle it is to cut JP15 on the clock line and use a jumper wire to pin PA7. I also have jumpers to connect A13 and A14 of the RAM to 2 GPIOs, so we can bank the RAM and quadruple the amount we can address with a single chip select signal. But of course, they'll be going to the breadboard for now. Now, cards on the table. What can we realistically get out of an SDR hooked up to a 6502? Well, back in the early 1980s, when the 6502 was king, the most widespread signal processing was probably DTMF, dual tone multi-frequency signaling. You know, the tones you hear when you dial a phone number. It's been around since 1963, but during the 1980s, most implementations had switched from analog filters to some form of digital signal processing, DSP. For DSP, you might have heard doing DFTs and FFTs are quite resource-intensive ways of analyzing a signal, but luckily we have Goertzel's algorithm. Instead of computing a full discrete Fourier transform, it evaluates individual DFT bins using a second-order recursive filter. Said another way, it only looks for specific frequencies instead of analyzing the whole spectrum, which is a lot more efficient way to figure out if a handful of tones are present in a signal or how strong a particular tone is. The algo does this by running the captured samples from the ADC through a filter. This design tip from ST has a pretty good example implementation. The trained eye might quickly notice it's simply the sample plus the previous product multiplied by a constant coefficient minus the product before that. The result is a number that grows relative to how strongly the input signal resembles a certain waveform. If it wasn't for the fact that 16-bit coefficients and products complicate things slightly on a 6502, the fact that we just need a single multiply by a constant we can pre-compute is almost too good to be true. I'm not going to go into details with the software I wrote for this demonstration, both because I spent more time writing it than I care to admit, and because it's not very well optimized. Very basically, it's just a 16-bit implementation of the example from ST with a shift and add multiplication. And right when I was just about finished, Charles Lohr, aka CN Lohr, who's known for getting the max out of cheap small micros, dropped by the Hackerspace Clubhouse on Discord and casually mentioned that if I'm doing Goertzels, I can even replace the multiplications with a combination of optimized pre-computed shifts, adds, and subtractions as ultra-fast fixed-point multiplications. Gotta love the math wizardry. I'll link his coefficient decompose calculator below, along with a link to GitHub for the 65Arduino code, of course. Currently, the SDR code lives on its own branch, so beware of that if you want to try it out. It still needs a bit of optimization, so feel free to help out with a pull request. Of course, the hardware is completely open source too over on its own repo. Since the plan to stack the modules fell apart, I've been using two 65Arduinos for development, one for the phase loom, which does the frequency selection and mixing, and one for the PhaseLatch, since it has wires going in every direction. I better make a new version with the fixed RAM footprint. I'll probably remove the non-functional RAMs from the current batch and sell the boards without them on my shop. They still make pretty cool ADCs without the RAM. That's spoilers for a future video though, but you might notice there's a footprint on the PhaseLatch for something else. So, what can it do? Well, I've added a few LEDs that are blinking pretty randomly at the moment. The signal coming from the signal generator and scope, currently off, goes through a 7 MHz bandpass filter into the phase loom that mixes down the signal with a 7.025 MHz LO down to baseband, which goes out through the twin 20 kHz low-pass filters into the PhaseLatch ADC, which saves a bunch of samples to the RAM and does its DSP magic, looking for a few specific tones and outputs the results to the LEDs. So the reason it's blinking somewhat randomly is it's finding the highest tone in the background noise since the scope is off. But if I turn it on, we should see it stabilize to a single LED, and the serial output should show higher values. The LED on the right represents a tone of 3900 Hz, and the leftmost one, 870 Hz, picked to be about 1 kHz apart. So approximately 1, 2, 3, and 4 kHz. Since the tone should be about 3900 Hz, we should expect the incoming signal to be about 7029 kHz. But as you can see, the signal generator is only set at 7027.1 kHz. Why? Well, we can verify the ADC on the PhaseLatch received the 3900 Hz signal, so that leaves the phase loom and the signal generator itself as the problem. And usually, it's the uncalibrated crystal on the phase loom responsible for the discrepancy. So keep in mind, the input signal looks 1800 Hz higher than it is. If I start reducing the frequency, we'll see the other LEDs light up. As you can see, it's a bit glitchy, but in general, we successfully detect the strongest signal. The thing is, there's still a lot to be optimized. The math isn't perfect, and I bet I have a rounding error somewhere, but as you can see, I did actually manage to make an SDR out of a severely limited 6502 platform. Is it 20 MHz bandwidth out of the ADC? Can it decode the whole FM band at once? No, absolutely not. The way the 6502 is bit banging the ADC clock means it's only about 28 kilosamples per second. Considering the 72 MHz Cortex M3 CPU with DMA and all the modern bells and whistles only managed to give us about 200 kilosamples, with USB being the limiting factor, I think the 1 MHz 6502 is putting up quite a fight. Though it's not exactly apples to apples. Running Gerald Goertzel's algorithm for tone detection on a 6502 is about the simplest software-defined radio job we can do and still call it a 6502 SDR. Keep in mind though that the RTL SDR, which is about the most common one, and doesn't do any of the DSP on device, but passes it all off via USB. So maybe it is fair game to just pass off all the samples to a stronger, bigger computer. What do you think? Should I do more SDR on the 6502? Should I try to get 20 MHz bandwidth out of this SDR first? Either way, thanks for watching.